of you for joining the first International Student Symposium on Basic Sciences. I feel great proud to say that the College University organizes such symposium and conferences and workshops to enlighten the young minds and promote the participation of the student at all levels. I would a very warm welcome to all the renowned speakers and delegates who took their valuable time and joined us today to be the part of this symposium. I am profoundly delighted to take the opportunity to introduce and welcome our today's speaker, Professor Ramos, from the Mathematics Applied Department, University at Sri Lanka. So before inviting him to the talk, let me introduce about the achievements of the Professor Ramos. Professor Ramos did his PhD from the University of Sri Lanka under the mentorship of Professor Vigo in the field of numerical analysis. His first contribution to the Congress was method of Falankar in the variable step and method based on the approximation by the Chebyshev polynomials to solve the second order initial value problem, and with which he obtained the PhD Excellence Award in 2004. Since then, he has investigated different numerical methods to solve the differential problems and in general on issues of the numerical analysis. He has published more than 120 articles and many of them in top rated journals and presented more than 60 talks at different national and international conferences. In last year, he was cited top 210% scientist of the world list published by the Stanford University. He has a part of scientific committee in the several international congresses. He has given guest lectures at different universities and his collaboration with more than 74 researchers from all over the world. His main contribution to the generation of the knowledge, first is variable step formation of the Chebyshev method to the solve initial value problem, variable step formulation of Falankar method to solve the second order initial value problem, development of algorithm to detect singularities in ODE, and many more. He has been a trainer tutor of the training program through practice in research and technology innovation for the university graduates. He has directed many doctoral and more than 30 final degree projects related to issue of numerical analysis. Currently, he is directing 2 doctoral theses. He has been responsible for the recognized research group of the university, scientific computation group, and also the academic editor of the various journals like mathematical problems in the engineering, Hindavi, mathematics MDPI, mathematics computer in simulation elsewhere, and differential equation and dynamical system of Spencer. He is also the editor-in-chief of numerical analysis and applicable mathematics. Dear participant, with such glittering and outstanding set of achievements, I feel it's our fortune to listen our today's speaker, Professor Ramos. Once again, I welcome you, sir. Before inviting Professor Ramos for today's speech, I would like to share that if any of the participant has a query during the lecture, he or she can either post it on the chat window, or I will recite all these at the end of this lecture, or one can directly ask in our question answer session. So now I would not want to stand even a single second more between you and our speaker. Sir, over to you. Professor Ramos, over to you.
Yes, I'm ready.
Yes. So please, sir, you can start your presentation.
Okay. So thank you for your presentation. Now I'm going to share my screen. Okay, I want firstly to thank the organizer for inviting me to this conference of Akal University. Particularly to Rajat and Professor Singh. I'm going to talk about the use of block methods for solving partial differential equations. Firstly, I want to make a review of how the block methods work. The block methods were firstly proposed by Milne. You can see the book where they appear for the first time, I think. It was 1953. And since then, there have been a lot of professors, scholars that have used these methods for solving different kinds of differential problems. Particularly such scholars as Champagne, Fatullah, Jator, Mahib, Brugnano, Simons, Cash. These are well-known professors that have worked on block methods. How can I define a block method? You know about the multi-step formulas, which are used for solving initial value problems, for example, that use information on different steps. So we can say that a k-step block method is a set of k multi-step formulas that gives k approximate values of the differential problem at k different grid points at the same time. So this means that we have a set of formulas. We have to solve this set, and as a result, we get the approximate solution of the problem at hand. Of course, this is a roughly definition and may vary according to the method we choose and the kind of equation we are considering. Let's see how it works for first order problems. This is a two-step block method. So you see that there are two approximate values, yn plus 1, yn plus 2. These are the approximate solutions of a given problem. This one, y prime equals f. Also, we have the initial value, of course. And we see that the method consists of two formulas. So in this case, we see that this is an implicit system because we have yn plus 1 and we have fn plus 1 here, for example, and yn plus 2 and fn plus 2. So we have two unknowns. And so to get this as known, we have to solve this system. Usually, the Newton's method is appropriate for solving this kind of system or any variant of Newton's method. Okay, this is a formulation of a two-step block method. But there are many more. In fact, if you look for in the literature, you can find, for example, those different formulations. In fact, they are the same block method. So they consist in two formulas, and you have to solve these two formulas, these systems, and you get the approximate values. So these are different formulations. Let's see how to develop any two-step block method. So we have an interval, a generic interval, xn plus 2. So we have 3 grid points. We assume that these are a uniform grid. If this is not uniform, it can be also obtained, but it will be a bit difficult. But it is not necessary. So this table informs us about the information we have. So we assume that the initial values are known. So we have yn is known, is a known value, a real number. Fn is also known. The unknowns are weight n plus 1 and weight n plus 2. So fn plus 1 can be expressed in terms of the variables, of course, and fn plus 2 can also express in terms of the variable. So the only variables are weight n plus 1, weight n plus 2. So we have two variables, and we can say we have 4 informations. That is 4 values we can use. So we are going to use approximations considering polynomial approximation. So as we have 4 values here in this table, we consider a polynomial with 4 terms. So the degree of the polynomial would be 3. The aj are knowns that we had to determine. How can we determine those values? Of course, using the information we have here, the 4 values I told you. So we evaluate the polynomial of xn. This is a known value. P prime of xn is also a known value. P prime of xn plus 1 is fn plus 1, but we assume that this can be expressed in terms of the variables, and also with the P prime xn plus 2. So we solve the system and we get the coefficients of the polynomial. The polynomial is an approximation of the true solution at the interval xn plus 2. So if we evaluate this polynomial at the values xn plus 1, xn plus 2, we get those formulas. Those formulas is the block method. One formulation of the two-step block method. You can do similarly for 3 steps, and in this case, you obtain 3 formulas, of course. There are different formulations of the 3-step block method. It depends on how you choose the unknowns. And for example, this one, the last one, is the same block, 3-step block method. But in this case, we have the fn plus 1, fn plus 2, and fn plus 3 explicitly expressed in terms of the other values. Which is the advantage of this formulation? Well, in the first one, you can see that f appears many times. Almost, 3 times at most in the formulas. But so if is complicated, the system would be more complicated. But in the last one, even if f is complicated, the system is more easy. Okay. Let's see how to obtain a 2-step Ivric block method. So what is the difference? We have also 2 intervals, so xn plus 2, on the grid point xn plus 1. And now we consider 2 intermediate points, one between xn and xn plus 1, and the other one between the rest of the 2 points. So now we have 1, 2, 3, 4 variables. So the values of the solution, of the approximate solution at the grid points and also at the intermediate points. We assume that the initial values are known, of course. And so in this case, we have 2, 4, 6 values, these ones, that we can use to get the approximate polynomial. So in this case, okay, these points, the intermediate points, you see where are located. So we consider that R is between 0 and 1, so that we have an intermediate point between the 2 first points, and S is between 1 and 2, so we have an intermediate point between the 2 second points, the second interval. Now, the polynomial is a polynomial of degree 5. Remember that we have 6 coefficients and 6 values to determine those coefficients. So we impose the conditions, and we have the yn is the approximating polynomial applied to xn, and well, this is the same with the other values. So we have a system with 6 equations, because we have 6 coefficients, and we solve this system to get the coefficients of the polynomial. Of course, the coefficients of the polynomial will be expressed in terms of the other unknowns. So we solve the system, we evaluate the polynomial with that coefficients we have obtained at the points xn plus 1, xn plus 2, we get the approximate formulas to approximate the true values at the 2 grid points. So we had, in this case, 2 intermediate values, and we had 2 parameters, R and S. So how can we obtain the values for these parameters? Well, one possibility is to consider the local truncation errors of the 2 formulas we have obtained. So we expand using the usual tool of Taylor's expansion in terms of powers of h, and consider the truncation error. So in this case, for the first formula, we have that the truncation error is given by this expression. And the second formula for the truncation error for the second formula is given by this. So we have that the principal terms for those errors are expressed in terms of the parameters R and S. So what we are going to do is to equal 0 these terms, the principal terms in the first truncation error, and also in the second truncation error. So we get an algebraic system. We solve this system, and after solving this system, we get, okay, this is a solution, but usually there are more solutions, but they are symmetric. So there is only one solution in this case, for which R is between 0 and 1, and S is between 1 and 2. So these values are 2 optimized values because we have used them to get better truncation errors. So we have increased the order of the truncation errors. Doing this, we obtain the rest of the formulas. So we evaluate the polynomial of xn plus r and xn plus 1, xn plus s, and xn plus 2, and we get 4 formulas. So these are the 4 formulas for those values of R and S. So this is the block method. So in this case, the block method consists of 4 formulas because we have 4 unknowns. So we solve the system, we get approximate values for the true solution on the, say, the first interval. We take 2 subintervals and solve again, and we take next 2 subintervals, we solve again, and so on. So this is a sequential procedure to get the solutions of the initial value problem. There are other possibilities. I'm going to show how to obtain a block methods for second order problems. In this case, we can also apply the block method for solving boundary value problems. So now there is a little, not so little difference. There's a difference with the application of a block method for solving initial value problems and for solving boundary value problems. So we can consider different boundary conditions, as we know. So we can have the values at the two endpoints of the solution, or we can have the values of the derivatives at the two endpoints, or we can have mixed values. So we can express this considering these two equations. Okay, let's see how to get a block method for a second order differential equation. And in this case, we are going to introduce a new aspect. And this new aspect is the second, not the second, in fact, the third, because it's a second order problem, the third derivative. So we have the values of the solution, the values of the derivative of the solution, the values of the second derivative. So these are the values of the f, since y double prime equals f. And in this case, J is the name for the third derivative. So we have the third derivative of the solution. So this is the first derivative of the function f. So we have this at our disposal. So we had to derive the f with respect to x, of course, and we have the third derivative. So in this case, we have four unknowns because we have two values of the solution and two values of the derivatives. We don't know these values. But in this case, we have 2, 4, 6 values to formulate the method. So we consider a polynomial with 8 coefficients. This is the polynomial to approximate the solution. And we impose conditions, again, at values. We get a system. We solve this system, and we get the coefficients of the polynomial. Now, the next step is to evaluate this polynomial at the points we want to be approximate. So we evaluate the polynomial of xn plus 2 and get this formula. So in this case, we have also the first derivative, which is an unknown. Sometimes we are not interested in these first derivatives because, for example, if you consider that this is a special second order equation where the y prime does not appear, so we don't need, okay, these values, we need these values because these values will appear in the formula for the next step. But the y prime m plus 1 is not necessary. So in this case, we can reduce the number of equations, and this will simplify the system. In this case, we have these two equations, and also we can formulate the values also for n plus 1. But as this would be the usual approach to be applied for solving second order initial value problems. So if you think that you have initial conditions here, you should have to obtain the values for y n plus 1 and y prime m plus 1. So in this case, you have 4 equations, you solve the system and you get the approximate values. But as we are going to use this for solving a boundary value problems, the procedure is different because we don't know the initial values. We know maybe an initial value on the first point and another value and the last endpoint. So we cannot use this procedure sequentially as we did before for initial value problem. Okay. So what we are going to do is to consider this formula, these two formulas, and we're going to take values for n equals 0, 1, 2, m minus 2. So n in this case is the total number of subintervals. If we apply here n equals 0, 0, 1, 1, 2, 2, etc., we get different values for the approximate solutions. So in this case, we get a total of 2 times n minus 1 equations. We have also two boundary conditions that we can consider two equations. In fact, if we know the values, so we have two unknowns less, and in this case, we also had two less equations because the values are known. But think, for example, in the third case, where we have a relation between y and y prime at the first point, and y prime at the last point. So in this case, we have a relation. So this is an equation. Okay, so we consider two more equations. This makes a total of 2n equations. If you consider, let's see, if you take n equals 0 in these formulas, you have y2 and y prime 2. So we need two more equations. These two more equations can obtain considering similar formulas for y0, y prime 0, or y1, y prime 1. In this case, for example, I have considered two formulas for y0 and y prime 1, prime 0. So these formulas, together with all the above formulas, gives a total of 2n plus 2 equations. So we have 2n plus 2 equations and 2n plus 2 unknowns. In general, okay, maybe we also have 2n equations and 2n unknowns. But in general, we will have these equations and these unknowns. So we solve the system and we get the approximate values for the true solution along the integration interval, along the grid points on the integration interval. So you see that this approach is different because we consider this can be considered as a global method. We get the approximate solutions at once, solving a big system of equations. Let's see just one example for this. In this case, this is a system of second order differential equations, and we have boundary conditions at the endpoints. So in this case, remember that for one equation, we will have 2n, a system with 2n equations. As we have here two equations in the differential system, we will have 2 times 2n equations. So we have to solve the system and we get the solutions. Well, these are the functions in the right-hand side of the differential system. These are the true solutions. And this is a table with the results obtained with this method I have shown to you, and compare with this method which appear in this reference. well, you see that the method, the block method, performs very well. So we obtain a very accurate result. This is the absolute errors for the first component and the absolute errors for the second component. This is a plot of the first component and the discrete solution obtained with the block method. So the points, the dots in red are the discrete solution, and the line, the continuous line, is the exact solution. So this is the same for the second component. I want to draw your attention here about an aspect which you can see that the errors on the first component are, the accuracy of the errors is less than the accuracy of the errors for the second component. If we look at the solutions, we see that the first solution was a oscillatory solution, and the second one was just a second polynomial, second order polynomial. So, in fact, if we have also that the first solution was a polynomial, okay, related with the order of the method, the solution would have been an exact solution. I mean, the discrete solution you get with the block method would have been an exact solution. Okay, not exact in fact, because there are some errors related with the operations, okay? But with truncation errors, but round off, maybe round off errors. But you see that these errors are, in fact, related with the order of the epsilon machine. So the method works very well. Okay, let's see how can we use the block methods for solving more complicated problems. In this case, I'm going to explain how to obtain a two-step hybrid block method. Hybrid means that you get intermediate points. For solving a second-order differential equation, but in this case, a part of the hybrid points, we are going to consider also third derivatives. But in this case, just two third derivatives. So at the first point and at the last point. As before, we assume that we know the values at the initial value, okay, at xn. You saw that this is different if we apply for solving boundary value problems, as I told you before. But we assume this here. So we have 2, 4, 6, and 8 unknowns. That is, the values of the solution and the values of the derivatives at the different points. And we have 2, 4, 6, 8, 9 values that we can use to get the approximating polynomial. So in this case, we consider a polynomial of 8 degree. We are considering 9 coefficients, and we apply, as before, the polynomial at the different points to get the approximate values. Okay, the values we are going to use to get the method and solve the system. We get the coefficients, we evaluate the polynomial at the different points and also the first derivative, and we get the different formulas, okay? In this case, we had 2 parameters. So we had to decide to choose how to obtain those parameters, values for these parameters. So we consider the local truncation error of the formula for the solution, the local truncation error for the formula for the derivative, and we solve. So we take this 10, the principal 10 equals to 0, and also this principal 10. We get a system. I want to say that this procedure to get values for P and Q can be different if you consider different formulas. Let's say if I had taken, instead of y xn plus 2, y applied to xn plus 1, that is the other value, the other approximate value at the good points. So I will have obtained another formula here. So the result would have been that we have obtained another method, okay? Another optimized method. But in this case, I have chosen to take the first. So I solve, because I chose the same in the first case I show you. So these are the values we obtain with this procedure. If you remember, these are the same values of the parameters we obtain for the other hybrid method for first order differential equations. Okay, these are very appropriate values. In this case, if we evaluate the polynomial of x plus 2 and substitute the obtained values, we get this formula. And also for the first derivative, we get this formula. So we have two formulas of the block method. Of course, we had 8 unknowns. So in case we want to apply the method of solving first order, not first order, sorry, the second order initial value problem. So we need 8 formulas. So these are the other formulas. So we have 6 formulas here. With the 2 formulas before, we have a total of 8 formulas. We solve the system and we get approximate values, and also approximate values for the derivatives, okay? Some of these values for the derivatives, maybe we are not interested in those values, and in some cases, we can eliminate some of the equations, particularly if the first derivative does not appear in the function. Okay, how can we apply this for solving boundary value problems? This is a little different approach as I used before with the other methods. So in this case, we take n equals 0, 2, 4, 6, etc., where n is an even number, in this case, because we are considering a 2-step block method. If we had considering a 3-step block method, n should have been a multiple of 3. But in this case, n is a multiple of 2, okay? So if we take n equals 0, 2, 4, etc., and consider the different formulas, we get a system that can sit on a global block method. Also, we include the boundary. We must include also the boundary conditions, of course. And so in this case, we have a global method to solve the boundary problem, the second order boundary problem. Okay, this is an application of this method, this last one, for solving this particular equation. Here there is some added difficulty because we have a singular problem. You see, we have an interval 0, 1. This is the interval of integration. But we have some problems with this x we cannot get. If you consider that this term, you pass this term to the right-hand side, this is the f. So you cannot evaluate the function f at the point 0 because there is a singularity here. Okay, this cannot be evaluated. So we cannot apply the block method in the present form. So what can we do? Okay, what we can do is just to consider a set of formulas for the first block. First block means x0, x1, x2, or even just for the first subinterval. And in these formulas, we do not have to use the value of f evaluated at x0. So we consider formulas evaluated at x1, x intermediate point is s, is r, x2. These formulas substitute the corresponding formulas on the global system where the f0 appears. So in this case, we get a system that we can use to solve this special problem that contains a singularity at the first point. So this is a table with the results with this method I have shown you before. Okay, the formulas for the first two subintervals are similar, and they are not put here. But this is a table with the solutions, the error, the absolute errors. So you see that they are very good with this scheme, and these are solutions with other methods appear in the literature. This one, number 3, is block method by Jator Oladejo, and this one is from Salan and he's added, which is a Euler-Galerkin method. You see that the block method gives very good results. Okay, and finally, I want to show you how can the block methods be applied for solving PDEs. So there are many possibilities that I am going to consider here, kind of PDEs where we have first derivative with respect to time and other derivatives with respect to space, space variable. So in this case, we can have first and second derivatives with respect to the space variable. We assume a rectangular domain. In this case, we need boundary conditions to have a well-defined problem and initial conditions. So we have two boundary conditions. So for x equal a and x equal b, we have along those lines those conditions, that is functions that depend on t along the integration interval, this one, and an initial condition, which means that at t equals t0, we have a value, and in this case, a function of x for x in a, b. Okay, this is our problem. To apply the block methods for solving this kind of problems, we're going to discretize the problem. And to do this, we consider a uniform spatial mesh. So we take values on the space line A, B. So, okay, we can take not only uniform spatial mesh, we can take also special meshes, non-uniform meshes, Shishkin, Bakalov, or any other Hain, any other mesh. But this is an open question that I have to investigate. But it is possible, yes? So in this case, we consider a uniform mesh. So this is the step size. What we are going to do is to approximate the spatial derivatives using the usual formulas to approximate derivatives. So for the first derivative, the usual formula, well, this is an approximation that uses values these 2 points. This is of order, second order. And this is the usual approximation for the second derivatives using 3 points. And is also of second order. Now, considering the mesh points, we said U, I, T as the solution applied to the mesh point xi and t for each of the mesh points. And also, we have those values obtained from the boundary conditions. So we discretize the problem, the PDE, using the approach for the first and the second order spatial derivatives using the above formulas. And so we obtain a system of differential equations. But now they are ordinary differential equations. So we have a system with n ordinary differential equations along the lines given through the grid points in the spatial variable. So these are the unknowns of the system, and what we had to do now is to solve the system using a block method. So we can use any other numerical method for solving the system, of course. Say Runge-Kutta method, say multi-step formulas, any other, okay? But the interesting thing here is that in many cases, this system is a stiff system, and not many methods are appropriate for solving a stiff system. But the block methods you have seen are implicit methods. So this implicit character is very interesting for solving this kind of problem. Okay, let's see how to apply for solving, for example, this well-known diffusion equation. So you have diffusion equation, you consider the second order derivative, you use the above approximation, and you get a system with ordinary differential equations. These are the initial boundary conditions that are necessary, because if you see at the approximate derivatives. For example, you take I equal 1. So you have here the function applied to x 1 plus 1, 2, and 1 minus 1, 0. So you have to apply the function x 0. So this is where you use those conditions, the boundary conditions, okay? And similarly for the last one. For the last one, and you have here n plus 1. So to approximate, well, not to approximate, because these are values because you know the boundary conditions. So to get these boundary conditions in the formula, you use these boundary conditions. You know the exact values there. Okay, so we have an ordinary differential system where we also need the initial conditions. So we need the initial conditions of t equals 0 to solve the problem in a sequential manner. And okay, we apply. I have not included tables here, but just the solution. So this is, I don't know, I have not put here the exact solution, but this problem has an exact solution. And this is the plot of the exact solution and the plot of the discrete solution we obtain with the block method. So you see that we have lines along the say along the grid points, okay, the spatial grid points that fit very well with the exact solution. There is some difficulties here at the end, because you can see that the first derivative is very high. So this is the steep and steep problem. In this case, you can see also that the discrete values along, say, for example, the first line, they are not equally spaced. In the time variable, they are not equally spaced. Okay, this is because, as you know, for solving a differential problem, it is better to use a method where you change the step size. So this is what I have used here. I have changed the time step size. This is not very difficult to do. You have to consider another formula. So with the two formulas, you get an estimation of the errors on each step. And this permits to get a new value and a better value for the next step. So you take two intervals, step H, and the next I am talking about a 12-step block method, and you decide which is the step size for the next two intervals, say H1, and you use this new step for the next two intervals, and so on, and you get a value. This is a better approach for solving differential problems. Well, this is another example. This is a Burger's equation. In this case, this is a nonlinear equation. So we have here the solution, the u, and multiplied by the first derivative. And in this case, also there is an initial condition which is non-smooth, because we have this is you see a line, this is a line, so they have a peak, and these are the boundary conditions at x equals minus 10 and x equals 10. So this is the region, okay, the rectangular domain. So this is the solution. Okay, I must say here, I want to draw your attention to one thing, and is that the conditions here are not consistent. as they are expressed here, because if you see for t equals 0, you have that u at this point, so minus 10, 0 must be 1. But if you look here, for x equals minus 10, it's 0. Okay, I was aware of this problem later, because I took this problem from an article, and it was not written, the conditions. These are not consistent. But it doesn't matter, because you can think that you have this function, and you can think that you have 1 at this point and 0 otherwise. So it doesn't matter. I can solve the problem equally. So this is the solution. So you see that there is no problem here. So this is the solution we get. And the errors are of the -7, so it means that it works very well. The Bookmaster equation is also a second, not a second, well, you have second order here, but you had u to the power 4 and u to the power 3 here. So this is a, well, nonlinear problem. In this case, subject to those boundary and initial conditions. And this is the solution. In this case, the errors are of order -10. As you can see in this case, the space variable is here. Okay, you see this is the x variable. So the no, it's here. It's here, the x variable, and they are equally spaced, and the time variable is here, and they are not equally spaced. You see that they are not equally spaced. Right? But the space in this direction, in the time direction, the step size is almost similar. Okay, these methods can be applied for solving 1D system or 2D systems, or many other problems, like this one, for example. What is the problem here? The problem is that the number of equations are going to increase, but okay, you have a good solver for solving the system, and now we have very good solvers, so you can solve the problem. Okay, some conclusions. The block methods may be applied for solving very different kind of problems, in particular PDEs. There have been many people that have been using, and now are using, the block methods can introduce intermediate points that can be optimized using the local interpolation errors. Well, there is an open research, this is the final point, about the use of block methods for solving efficiently singularly perturbed problems using non-uniform meshes. So this is an open research for the future. This is some bibliography. Okay, that's all. So thank you for your attention.
So thank you, Professor Moos, for wonderful lecture on the block methods and their applications. Now the session is open for the question answer. As symposium is in hybrid mode, so I request the participant who joined us on online mode, they can either paste their question in the chat window, or they can raise their hand. Okay. Now, in the case of offline mode, I request Mr. Rajat Singla to help me in getting the questions from the audience. So, audience, please.
Yes, Payal.
So please come forward to ask your question.
Actually, Manray Soul isn't here. Sir, my query is that as you have deduced a plethora of methods there, So what are the precedences of using block structures in those methods? Using of block structures in those methods. Advantages of that. Am I audible, sir?
Advantages of using block methods.
Yeah.
Well, I told you that one advantage of using block methods for solving, for example, PDEs is that they are usually the system you get is usually a state system. So as the block methods are implicit, they are very useful solving this kind of problems. Another advantage could be that you do not to use predictor, because, for example, you use methods in predictor corrector form, that is implicit formulas where you use as corrector the implicit ones. So you need predictors. So you had to do more evaluations. But in this case, you do not need predictors. So this is another advantage. And the last one possibly is the use of variable step size. Variable step size is very useful for solving problems where you have different behaviors. So you have parts where there are smooth gradients and parts where you have higher gradients. So in this case, the use of methods that use variable step size is very, very indicated. And the block methods can be implemented in variable step size, not very difficult. Okay, it is not very complicated.
Thank you, sir, for the answer. Yes, anyone else? Yes, please.
Good afternoon, sir. So my question from you is, R and S in these PPTs. So what are the benefit of this? As you have used R and S in your PPT, so what are the benefit of this? That intermediate points, what are the benefit of this?
The intermediate points. Okay. Yes. The use of intermediate points is to get higher order methods. So, because you have more information at your disposal. So when you consider intermediate points, you get higher order methods. So they are expected to get better results. Usually, these methods have very good stability characteristics. So they can be applied for solving state systems.
Thank you, sir. Anyone else?
So my question is, in this approach, the method is constructed using the approximation of true solutions in the form of polynomials. Can we have any other representations as well?
Yes, of course. In fact, there are other forms you can use to get approximate values. There are some block methods that are especially designed for solving oscillatory problems. So if you know that the solution of your problem is oscillatory, you may use adapted methods. In this case, trigonometrically adapted methods. So in this case, you consider that the approximate solution is given by some polynomial terms and some terms including cosine, sines, etc., depending on what or problem you had, or exponential terms. So yes, it's possible. In fact, there are methods of these types, block methods.
Thank you, sir. Anyone else?
Good afternoon, sir. What is the advantage of using multi-step method over single-step method?
I think the main advantage in using these methods over the one-step methods is that you get at the same time different values. So I think that the main advantage is the computational time. Apart that the block methods are, in general, they are good methods. They have very good characteristics. So apart of this, I think the computational time.
Thank you, sir. Anyone else? Yes, please.
The construction of first method, you have used 3-degree polynomial. As it is, you have used polynomial.
Sorry, I didn't understand.
In the construction of first method, you have used 3-degree polynomial. Can we use higher degree polynomial?
Oh, the degree of the polynomial you use to approximate the solution is related with the information you have. So if you want to use a higher degree polynomial, you must consider more points. So you can take 3 points, 4 points, or intermediate points.
Thank you, sir. Anyone else for the query? I think, sir, there are no queries. You can read the chat box if there are some queries.
Thank you, Rajesh, sir. Sir, there are some questions from chat box. First question is, what are the real life application of PDE, partial differential equation? I think students are asking for some interesting real life application.
The application of PDEs?
Yes.
Well, the application of PDEs, you can look for many applications. The heat equation, the wave equation, there are the Borger equation, Buckmaster equation. So there are many things in physics and in mathematics also, but in physics and other disciplines where you can apply partial differential equations.
So thank you, sir. Next question is, this is last one. What is the Burger equation and why it is called Burger equation?
Sorry, can you repeat?
What is the Burger equation and why it is called Burger equation?
Sir, actually they are asking about why it is called it as a Burger equation in PD.
Because Borger equation is the name of the person who designed this equation. You can look in Wikipedia and you find information about the Borger equation.
So
Thank you, sir, for all the queries. Now, actually, I want to ask, sir, one query from my side. Hope I am audible, sir. Am I audible, sir?
Sorry, did you hear?
Sir, am I audible to you?
Sorry, I can't hear. Are you speaking?
Professor, am I audible? Maybe there is some network issue. So am I audible, sir? Professor Ramos, am I audible?
I can see you, yes.
So my voice is coming or not? Hello?
Hello, I don't understand, sorry.
So am I audible,
I can
sir?
hear you very bad.
Yeah, please, sir, please ask your question.
Am I audible, sir?
Okay, maybe you can, I don't know if you are asking something, but maybe
Yeah,
you can put in the chat, maybe.
Okay.
Because I can understand.
Then definitely, sir, I'll ask you later. No issues. Proceed the session, please.
So I think there is no more questions. So let us thank our today's speaker, Professor Mose. So my heartfelt thanks to you, sir, for sparing your valuable time and delivering an insightful, insightful knowledge-filled lecture. I am certain that our participant has had much knowledge to take away from this expert talk. So thank you, sir. Thank you once again. And now, audience, so this session is over, and we will meet in the next session. And thank you, sir. Thank you for your time. And
Okay, thank you very much for your invitation. Bye.